Hey everybody, today we're checking out similar figures. Okay, so similar figures, a couple attributes about them here. So first thing, the figures are going to be the same shape. So like you might have two triangles or two rectangles or two trapezoids or whatever. So they're the same shape, but they're not the same size, right? They're similar. So they look the same, but just one will be bigger than the other one. And then corresponding angles are going to be equal or congruent, we could say. So the angles in the same corners would be the same size. And then the corresponding sides are proportional. So I'll show you what I mean by that. First of all, we have two triangles here, right? Triangle ABC and triangle DEF. So what we can say when two figures are similar is we can say they are similar to each other using this symbol there, like the little squiggly. So like it says right here, notice that the similar symbol is that. So when you see that between two things, it means that they are similar. So they're the same shape, just different sizes. Okay? So when you look down here, if triangle ABC is similar to triangle DEF, that means we can kind of match up these sides, right? So like if I look at side AB and side DE, that's like this right here. I'm comparing the small one over the large one, right? So 5/10. Okay. I can compare that with these other ones too, right? I could say side BC with side EF, that's this middle piece. The small over the large, the 2 over the 4. And then I have this one, right? Side AC over side DF, that's this, right? So what you'll notice is, like it says here, the corresponding sides are proportional. That means each of these ratios we created, they all simplify to 1/2. 5/10, 2/4, 4/8. They all simplify to 1/2. So you should see that happen with a similar figure. Down here it says in the diagram, triangle DEF is similar to triangle MNP. So we have to find the value of x. So in order to do that, we have to set up a proportion. Okay, and then like it says right here, consistency is key. That's the number one most important thing when you're doing similar figure problems. Okay, so we have to find x, right? So we're looking for this. So let me just highlight this right here. Okay, so we're looking for that side EF. So I know I have to compare it with this side NP because those are the corresponding sides, right? In order to set up a proportion, I need 4 things in my problem. Those 2 green sides are 2 things, so I need to pick another set of corresponding sides to compare it with. So I'm going to also use ED and NM. I could have, if I wanted to, use these 2 sides, doesn't matter, but I just need to pick 2 that are corresponding. So when it says consistency is key, this is what it means. If you're putting, like if I do x over 20, right? That's this over this. I did small over large. Small over large, right? So that's this right here, small over large. So I need to do small over large for my second one. So I'm going to say this equals small blue side was 9 over large blue side was 12. So now, again, this is my small x, right, over the large. Whoop, sorry, somehow this got erased. So I've got my small over the large, small over the large. Has to be consistent. Okay, so if I've got it set up correctly, now I can just cross multiply, or I can find a pattern to like get to x. Here, I'm just going to cross multiply. So I'm going to say 12 times x is 12x, right? Bring down my equal sign. 20 times 9 is 180. Divide both sides by 12. Okay, so 180 divided by 12, you should get 15. So for this problem, we're going to say that side x should be 15. Okay? All right, let's go down here. 2 triangles are similar. Use a proportion to solve for the missing side. Okay, so this is kind of like the original problem, right? Like these two triangles with the black outline. What I did was I rotated this one 90 degrees to make it look like this, so it kind of matches what this looks like. So it might be easier to think about, right? So sometimes you might have to take one of the shapes and rotate it a little bit to make it look like this one over here. So I did that here, right? So I'm going to find x. So I have to find this blue side. So I'm going to compare it with this bottom blue side. And then I need to pick another pair of corresponding sides. So we'll do this one and this one. So we're going to do, I'll just keep it the same as we did the last one. I'll do small, so 3 feet, over the large blue side, x feet, equals the small green side over the large green side. Right? So if this is my small one and this is my large one, this was like small over large, small over large. It's consistent. That's the key. Okay, so now I'm going to cross multiply here. 5 times 3 is 15. X times 2 is 2x. Divide both sides by 2. You should get x equals 7.5 feet. Right? All right, so real life example, right? Where would you actually use this in real life? And this seems like a skill where you'd think like, this is never going to come up. But there's some times where this might come in handy, right? So one thing is with indirect measurement, and it's used to measure things that are hard to directly measure, like a tree height, for example, right? It's kind of tough to just go measure a tree, right, for a typical person. But if you know some other information, you can get a pretty good guess of how tall a tree is or a building is or whatever, any kind of large thing. So it says, a person that is 5 feet tall casts a shadow that is 4 feet. And they're standing next to a tree that has a shadow of 10 feet, right? And then the question is, how tall is the tree? So my person here, they're 5 feet tall. Whoops. They're 5 feet tall. They have a 4-foot shadow, right? Over here, the tree has a 10-foot shadow, and I'm trying to figure out how tall is this thing. So if you know how tall you are, you can at least estimate or maybe even measure your shadow, and you can measure the shadow of a tree or some other large thing. You have 3 out of the 4 pieces for a proportion, and you could pretty closely get the height of that tree. So I'm going to take the height of the person over, right, the height of the tree. So we'll say that's the tree is x feet. Then my second ratio will be all about the shadows, right? The length of the shadow of the person and the length of the shadow of the tree. Okay? So, cross multiplying here, we're going to get 50 equals 4x. Divide both sides by 4. Okay? So you should get x equals 12.5 feet. That would be a good estimate of how tall the tree is if you know all those other things. So it comes in handy sometimes. Okay, down here. So scale factor is something we can figure out with similar figures. This is the way you want to do it always when you do scale factor. You put the new measurement over the old original measurement. Okay? So scale factor, right? We've got 2 similar figures, 2 similar triangles. We're going to put the new over the old. Now it doesn't matter which set of corresponding sides you use. So maybe I'll just use these 2, right? On the new one, it's 15 units. On the small old one, it's 10 units. So if I do 15 over 10, and I simplify it down, I divide it, I get a scale factor of 1.5. That means that the new one is 1.5 times the size of the old one. It's 1.5 times bigger, right? If something was 1 times as big, it'd be the same size. If it's 1.5 times bigger, it's getting larger, right? If something's less than 1 time the size, it's shrinking. So down here, the scale factor of parallelogram ABCD to WXYZ is 4. Okay, so that means here's A, B, C, D. Here's W, X, Y, Z. It's a scale factor of 4. So you're going this way. And that means you multiply each side by 4, right? 4, that's bigger than 1. That means it's getting bigger, right? It's like 4 times the size. So like this side right here, AB is 5 on the small one. It's 20 on the big one. That's 4 times as big. And same with all these. BC is 4 on the small one. It's 4 times as big on the big one. It's 16. But if I went the other way, the scale factor of parallelogram WXYZ to parallelogram ABCD is 1/4. That makes sense because this is smaller than 1, so it would be shrinking as it goes to that small one. So this side, right, this like WZ 16 unit side, that is shrunk down 4 times when you get to the small one. So 1/16 times 1/4 is really just like dividing by 4. That's like the same thing. And you get 4 over there. So when you get bigger, you scale up. When you get smaller, you scale down. And like we just said, when you're scaling up, the scale factor is going to be larger than 1. When you're scaling down, the scale factor is going to be smaller than 1. It's going to shrink down. Okay? So scaling up is like if you're looking at like either using a microscope or some other sort of like here it's like an optometrist looking at people's eyes, anything that they're enlarging to see a bigger version of, right? That would be scaling up. When you're scaling things down, sometimes we call that a reduction, right? That would be like the solar system. It was reduced so we can study it here on this chart, or like the weather radar, right? It's not, the weather in the States aren't actually this big. We shrink them down so we can see it. So let's go down here. Let's try a couple practices. So we're finding the missing side, and then we're finding the scale factor. Okay, so let's start by finding the missing side. I need to compare 2 sets of congruent sides, corresponding sides, right? Not congruent sides, corresponding sides. So here we're going to say 12 and 3 would compare. 20 and x would compare. So I'll do 12 over 3 equals 20 over x. Cross multiply. You get 12x equals 60. Divide both sides by 12. And you should get x equals 5. So this right here should be 5 units long. Okay, remember, consistency is key. Now we have to find the scale factor. So we want to follow this. The new copy over the old original. So I can take any 2 sides. So let's do 3 on the new over 12 on the old, right? If I simplify this down, I divide the top and the bottom by 3, I'm going to get 1/4. Okay, so my scale factor is 1/4. This is smaller than 1, and that makes sense because I started with something big and it shrunk down, right, to something small. So since this is less than 1, that makes sense. I'm shrinking it down. It's like I'm multiplying each of these sides by 1/4. Or I could say I'm dividing each of them by 4. That's the same thing, right? Down here, missing side and then scale factor. So let's do this again. So I could say, let's do this. 10 and 40 we can compare. 3 and x we can compare. So I would do 10 on the original over 40 on the new equals 3 on the original and x on the new. All right, so you should get 10x equals 120. Divide by 10. You should get here x equals 12. So this would be 12 units here. Scale factor, new over the original. Let's just use that 12 we just came up with. So we'll say 12 over 3. Those 2 yellow sides, we can match them up. 12 divided by 3 is 4. So this is a scale factor of 4. The copy is 4 times as big as the original. Each of these numbers are 4 times as big as the original thing. Right? Let's go down here. There's 2 more to look at. So one more example. right? Missing side, then the scale factor. So we'll compare these two sides. We'll compare these two sides. So I'll do x over 8, the new over the old, equals the 4 on the new over the 16 on the old. Now this one I could do cross products, or I could just see that 16 divided by 2 gets me 8, so 4 divided by 2 should just get me 2, right? I can kind of see that pattern there. So x is going to be 2. Now for the second part, I put the copy over the original, so 4 over 16 simplifies down to 1/4. So I would take the original thing, right, and I would scale it down. It would go down because each 16 times 1/4 is 4, right? Okay, down here, last thing. Are the two figures pictured below similar? Why or why not? Figure on the left is the original, figure on the right is the copy. Okay, how do we get our answer? Okay, so first thing is this copy is kind of rotated a little bit. So we can redraw this to make it easier if that helps. So I'm going to do that here. Okay, so this side here, right, is getting, I kind of just flipped this thing down, right? I kind of flipped the whole thing down like this. Okay, kind of like if I held right here and I just took this side and like folded it down. And then I reversed it, right? So this would be matching up with this. This would be 15. So these sides would kind of match together. This 8 and this side would match together. So that would be my 8. And then I could say like this 17 would match with this. So that would be 17. Okay, I'm going to erase the highlighting in case it gets confusing. Oh, whoops, I erased everything. Okay, now we have to say whether it's similar or not, right? To test this, we have to make sure each set of corresponding sides give you the same scale factor, right? So I'm going to do my new over the old to test this for each one. Okay, let me erase the rest of these highlights just so, again, we don't get mixed up. Okay, so I'm going to say the new 17 over the old 34. Okay, so let's see that. 17 over 34. Well, if I reduce this by 17, I would get 1 over 2. Okay, so our scale factor is going to be 1/2 there. Okay, let's see if the rest of them give us the same thing. They have to be the same in order for it to be similar. Let's look at these two. Okay, so the new 8 over the old 16. If I reduce by 8, again, I get 1 over 2. So it's looking good so far. Let's do the last thing. 15 and 30. Okay, so the new 15 over the original 30. I can simplify by 15. That's 1 out of 2. So since everything simplifies to the same scale factor, I could say, yes, these are similar figures. All right, thanks, guys. See you later.